Okay, this is a video for college algebra and the unit pertaining to the review. Now, this video is about radicals and simplifying radicals. And I'd like to reference you over to another video on the channel under the Math I Like playlist for the proof of the fundamental theorem of arithmetic, because we're going to use the result from that very, very heavily in this sort of context. Now, square roots are obviously very simple. We memorize these when we learn our multiplication tables. We've got all the numbers that are multiplied by themselves to make something else. So, for example, 4 is 2 times 2, 49 is 7 times 7, and so on and so forth. But a lot of times when we're doing Pythagoras or any of the things that we're stuck doing in college algebra or even geometry for that matter, we end up with these square roots that don't have a nice just simple square root that we can type in. And so what happens typically is you come over to your calculator and you type in square root of 8, excuse me, I typed alpha, square root of 8, and it gives me some really nasty looking decimal like this. Now, the problem with that is that when we start rounding, our answers get less and less exact and the errors compound. So most of the time in algebra, we would like to give what we call an exact answer, which is an answer that doesn't have a whole bunch of decimals on the end. And the way that we do that, we're going to use the result from the fundamental arithmetic and the fundamental theorem of arithmetic, excuse me. So the fundamental theorem of arithmetic states that every number is either itself prime or it can be written as the product of prime numbers. Now, in this case, I have 8. Notice that I can break this down into 2 times 4. Now, moreover, I could break this down another step and do this as 2 times 2 times 2. 2 is prime, and there are 3 prime numbers multiplied together, so 8 can be written as the product of primes. That's what the fundamental theorem states. Now, when we're trying to simplify these things, we may not always want to go down to the level of having the prime factorization. We may want to stop here, for example, because what I'm looking for are numbers within my factorization of 8 that have a perfect square root. So we know that 4 has a perfect square root, and because this is the square root of a product, I can write it as a product of the square roots. So that means I can take the square root of 2 and the square root of 4 separately. Well, the square root of 4 I know is 2, and then the square root of 2 does not have a perfect square root, so I can write this particular radical as 2 square roots of 2, and that is its simplified form because I do not have any perfect squares among the factors of the radicand. Now, I can do the same thing over here with 32. I can break it down. I can say, well, 32 is 16 times 2. Now, I do want to illustrate the point that this is a prime number. So notice that this would be 2 times 2 times 2 times 2 times 2, or 2 to the 5th power. So 32 can also be written as a product of primes. That's what the fundamental theorem says. But remember, we may not want to go this far. We may want to just look at the factorization of it and say, look for numbers that have a perfect square root, i.e. 16. So 16 has a perfect square root, and since this is the square root of a product, I can do the product of the square roots. So I can handle them separately. What is the square root of 16? You'd answer me 4. What is the square root of 2? Well, we don't know, so we're going to write that as square root of 2, and we see that the square root of 32 is 4 square roots of 2, like this. This can be done with larger numbers, for example, the square root of 80. Now, in the square root of 80, we have to get kind of creative here. One alternative way of doing this, if you don't like the factorizations and looking for numbers that have perfect squares, we can make a tree. Some people really, really like this. So I'm going to do 8 and 10 as the starting branches of my tree. Notice that 8 times 10 makes 80. Well, then, 8 breaks down into 2 times 4, and 4 breaks down into 2 times 2, and 10 breaks down into 2 times 5, and notice that along the outside branch of this tree here, meaning all the branches that do not have anything coming off of them, that's my prime factorization, 2 times 2 times 2 times 2 times 4. 5, excuse me. I'm looking at the 4 and pointing at the 5. So 2 times 2 times 2 times 2 times 5 is your prime factorization of 80. Now with the tree, what we can do is we can actually determine which numbers that we will write down outside of the square root. Now in a square root, for every pair of numbers in the outside little bubble there, for every pair of numbers that are exactly the same, I can write that number down once on the outside of the square root. So notice I have a pair of 2's here, so I can write that down once. I have a pair of 2's here, so I can write that down once. Then I'm left with a 5. 5 doesn't have anything, so we're going to have to leave it inside of the square root symbol. So I have 2 times the square root of 5, which is 4 roots of 5. Now, the reason that this tree thing is important is when we start dealing with higher roots. So I'm going to show you what happens in the context of variables, and then I'm going to go forward to roots that are bigger than square roots. So things like cube roots, things like fourth roots. Okay, let me just move it up real quick, and then I'm going to start this problem right here. So here we have a square root of 196 times x squared times y to the third. Now, again, there's a prime factorization for this, but we have variables here. Now, 196 is a tricky one because it's one of the numbers we're supposed to recognize has a perfect square root. So this is actually kind of deceptively easy. Notice that we have 196 times x squared times y to the third. So this is a square root of a product, so I can do a product of the square roots. The square root of 196 is just 14. Then I have to handle the x squared and the y to the third part, and that's where this tree business is really, really nice. So notice that if you break x down, you just have x times x. There's exactly 2 of them, and so I can take that out and write it as a singleton. So y to the third is going to be y to the second times y, and y to the second is y times y, and I'm kind of making it really small, but you get the idea. So there's one pair of numbers that's exactly the same, and then one kind of leftover guy that doesn't have anything to pair with. So when I write this down, I guess I should bring this down further. We'll have 14 times x times, I had a pair of numbers, so I can write a y on the outside, and what was left on the inside was a singleton y, and we write that down as square root of y. And this is your simplified answer. Now, in the context of higher roots, the same thing is true of the way that we started this video, where we were looking for numbers that have a perfect square root. The problem is that now we're looking for numbers that have a perfect cube root, and really the cube roots get so big so fast that most students don't just memorize these. There's a couple that are extremely common, for example 125, 8, 64, but much bigger than that, they get really difficult to identify. So this kind of thing is where that tree diagram is really, really nice. So here I'm going to have 5 and 100. Well, 100 is 5 and 20, and then 20 is 5 and 4, and then notice that 4 is 2 and 2. And what lives on these outside kind of branches that have nothing coming off of them, that's your prime factorization for 500. Now, here I want to show you kind of the way that you can tell if you can write it outside of the radical or not. So I've got 5 to the third power, because there's 1, 2, 3 5s, times 2 to the second power, and this is inside a cubed root. Okay. So what the square root symbol has is a blank space right here in this little elbow, and that indicates that it's an understood index of 2. The index on a cubed root is an index of 3. So that means that any power that we can write that is to the third, we can simply write that as a single copy on the outside and leave everything else on the inside. So I have 5 cube roots of 4 as my simplification for this guy. So another way to say that is notice that in a cube root, it requires not just pairs to be written outside of the radical, but it requires triples to be written outside of the radical. So I have a triple of 5, so I can put that outside of the radical, but I only had 2 2s, and so I have to leave those alone on the inside of the radical.